Welcome back to Conquering the JavaScript Interview. We're journeying through the maze of JavaScript, algorithm by algorithm, ensuring that you're prepped and primed for that crucial interview. And today we're going to unveil the secrets of the Interpolation Search, a method that goes beyond binary and estimates the position of the search item. So we're going to be finding that exact spot in our array. Let's interpolate! But first, don't forget to check out the description down below for a link to our community membership where you get access to not only our Discord community, and you can get real-time help from me and my co-instructors and other co-workers here at Covalence. You get access to our front-end and back-end courses when combined build our full-stack program, as well as my standalone React course and any future courses I add, which I'm in the works on a few right now, although I need to hone in my scope and focus a little bit more. So if you have interest in that, it's $25 a month. The link can be found down below. Otherwise, enjoy this video and let's get coding. So the interpolation search, I'm going to have a link as well in the description for the last video in this playlist, which is the binary search. This interpolation search algorithm is kind of inspired by humans can naturally search a phone book, and I realize some of y'all may not know what a phone book is, showing my age here a little bit, but y'all know what a dictionary, I hope, is, and it's more akin to how a human will actually go through that. So if you remember from the last video in binary search, we picked a midpoint, split it into halves, determine which half to go further looking into, split that in half, and etc. A divide and conquer approach. We're taking a similar approach here, but rather than picking an arbitrary midpoint, we are going to estimate a position based on what we know and then search from there. That's the same way we're going to look in a dictionary. Like in the previous example, if I was looking for the word falafel, I wouldn't just go, okay, well, let's open up to the middle of the dictionary and start searching from there. I would go, well, I know falafel starts with an F, so how about I just kind of flip through and find the Fs, and then I begin going, okay, well, am I in the FLs or the FAs, so I know where to hone in my search from there. We probe a spot somewhere in the dictionary where we think falafel is going to be, and then we begin searching for it from there. And that's what this algorithm aims to do better than binary search, right? It estimates the position of the item and searches from there. It works in the principle of estimating the position of a target value rather than a midpoint like in the binary search, right? So we're going to start with calculating an estimated position, and I'll go over the logic of that later on, rather than the middle. We're going to say if that position contains the desired item, great job, return its index. Otherwise, we're going to adjust, just like in binary, the range of either the left or right-hand side of our estimated position based on the comparison results, and then we're going to re-estimate the position. And then from there, if it's out of range or the value is not in the list, we return if it's not present. So basically, we keep on separating left and right-hand results, adjusting our range and estimating until we find our guy or gal, our element, our value, whatever it is in this array of data. Now, there are, just like with binary search, pros and cons. This is not just some upgrade from the binary search going, oh, if I know how to do this one, I can just ignore the previous one, right? Not without the magic word. So this is very efficient on what we're going to define as uniformly distributed lists. It has a better average case time complexity than binary search. Estimating is a really cool concept to know how to do and how to add to your code base. Again, if you memorize the formula, that's going to be a pretty good starting point. So instead of simply dividing the list in half, it makes a calculated guess. We're going to see how we can do that. And another pro are favorable scenarios. It works well when the elements are, again, uniformly distributed, which I'll define here in just a moment. But again, that on the flip side, if the data is non-uniform, the search might become inefficient and binary may be a better way to go anyway. The interpolation formula adds a bit more complexity than a simple midpoint calculation, because that one wasn't too bad to understand. The formula for the estimation point we're going to talk about is a little bit more complex, so a little extra overhead right there. And then we have the ability to overshoot, right? Because the estimation can overshoot and hence might need additional adjustments from there, but I'll show y'all a great starting point for understanding this algorithm. Even if you never implement it, remember, a lot of these are for just passing interview questions and understanding some computer science theory and stuff like that for you. So uniformly distributed data refers to a distribution where each value in the data set has an equal likelihood of occurring. That is the big thing to remember. Each value in the set has an equal likelihood of occurring, right? So in graphical terms, if we plot the data, it will form a flat line indicating an equal probability for all values. To think about this, think of a classroom where every student has an equal number of candies. If you were to chart the distribution of candies per student, it would be a flat line because every student would have the same amount of candy, hence a uniformly distributed data set. Other examples would be rolling a fair, not loaded, six-sided dice, or die. The probability of each number, 1 through 6, appearing is exactly 1 out of 6. It's an even distribution of the data, right? 6 sides, all can evenly appear. 1/6 is not weighted in any way. Tossing a coin, chances of getting heads or tails are both 50%, or like a raffle, where each ticket drawn has an equal chance of being drawn. Those are all uniformly distributed data sets where this algorithm is really going to begin to shine. So on the flip side, we have things like non-uniformly distributed data, where some values could occur more frequently than others, right? So that's going back to our classroom analogy. Instead of every student having an equal number of candies, imagine some students have a stash of 20, some students have only just 2 because they've eaten it or haven't gotten enough. We notice peaks, we notice valleys, students with more candies and students with fewer candies, and in that case, we have a non-uniformly distributed data set. Things like income distribution, age of retirement. A lot of people will retire between 60 and 70. Some might skew kind of early, 40s, 50s. You got some, real lucky folks. You got some not so lucky folks, or just people that like to work and contribute in some meaningful way, which means they might be retiring, whether through choice or otherwise, a little bit later, like late 70s or early 80s, right? So again, that's not a uniform, it is a non-uniform distribution of data. And then, friends on social media platforms. I don't really use them, so I have like 2 or 3 friends max on some of my social media platforms. There's other individuals that use these for their work or for enjoyment or for addiction purposes. They may have thousands of friends compared to me. So again, non-uniformly distributed data, just so you have an idea in your mind of what the distinction is between the two, which is the keyword uniformity, right? Remember, does it have an equal likelihood for every value, or does it not have an equal likelihood for every single value? So think dice, or think like age of retirement as the 2 examples if you had to give them, say, in an interview or something like that. So without further ado, let's actually start coding this sucker out and talking about how its logic works. If I have time for a recursive solution, I'll go over it, but it's again the same thing where it's how do we take an iterative solution loop and convert it to a recursive solution. Worst case scenario, I'll have it linked in a CodePen available in the description below this video. Okie dokie artichoke. So we have our interpolation search, and again, I gave you all 2 inputs here, which you can copy these from the CodePen as well. I'm going to try and include that more often for these videos. That just says implement this interpolation search algorithm, just something we're going to memorize how to write or be able to work our way through in an interview. We have a couple of input arrays with target values and return their index position. Remember, not the value, it returns the index position of that element. So again, for display purposes, I got my console clear for my auto restart feature here in my script. And let's start with this thing. We have our array input and our target value as our 2 parameters to this array. So just like in the previous example, we're going to have to calculate a low and a high, and we're going to initialize these values just like in our binary search. We haven't adjusted any values yet, so the entire data set is what we're working with, aka the beginning of the array, index position 0, and the end of the array is our high value, aka our array length minus 1 to get us that last index position. Now we have no idea how many potential iterations it could take to find our element value in this array, our target, which means we're going to be using a while loop instead of a for loop. Really good for a non-determined amount of iterations. I know, Eric, go away. I should just not do that until I'm done. Or I need to turn off autosave is what I got to do. There we go. That way I stop messing up this console window over here. Ignore this. Ignore this. There's nothing to see here, folks. Okay. So here's where we get a little bit fun in our condition. We have to continually have the search interval as long as our low doesn't surpass our high. So we're going to say as long as our low doesn't surpass our high. This looks a lot like the binary search one, which it is similar. Again, if the low swaps with the high, our range is out of whack and we probably don't have it, which means we can have a good idea that we're done looping here and we can return like we did in our last video. Let's say return -1 is going to represent the case where we don't find the index of our target value given the input array. So -1 is going to say, I don't think it's here, boss, and that's what that's going to represent. So if that while loop terminates and we have nothing else to do, it probably doesn't exist. So we're going to say -1. Now, like I said, low doesn't surpass the high. If our target is greater than or equal to the current minimum value, okay? Target, the one we're looking for, if it's greater than or equal to the current minimum value. So we're going to say, if our target is greater than or equal to our current minimum value. So we're going to look into, why did I typo that? There we go. If we look into our array at our lowest current value at this index position in our range that we're searching, and if our target's still greater than that, that means we're going to keep going because we're in that potential range, right? And then the opposite or the flip side of that is if our target is less than or equal to the current maximum value. So we're going to say if our target is less than or equal to the array at our high maximum value. So again, so long as low doesn't surpass high, as long as the target is in range, aka greater than or equal to the low value, and in range, aka less than or equal to the high value. That's what that's going to represent right there. So again, this ensures that we don't search outside the valid range or outside the minimum and maximum possible values. Okay, there's no point in searching outside of those. Once we're honing in our range, if we go outside of them, probably not going to be there. So that's what we got going on here in this little snippet of code. So here is what we're going to say, right? We're going to say if our low point is our high point, right? So basically, if we get to the point before this loop terminates, and we get to a point where our pointers, our high and low and high range pointers in this array indexes and these array indices, if they are the same value, we have to determine, well, we have one thing left to check. If this is correct, we return one of these because it's the same thing, low or high. But if they are not a match to our target, then we are missing, we don't have a value that can help us. What I can say is if, watch this. We're going to say if, we're going to do a shorthand, return low. Otherwise, we're going to return -1 because it's not a match. So basically, if we dwindle it down to where our two range pointers in the array go on top of each other, we're out of values to search in a range, which means we have to check to see if they're a match or not. So we're going to just pick one. We're going to pick low because if they're the same, it doesn't matter which variable we pick. I'm just going to pick low. We're going to pick that low value, and if it's our target, boom, we have our index of this possible case. Otherwise, we return -1 because, hey, this entire range has gotten to this point and we haven't gotten anywhere else, and we can just return -1 and call it a day. So that's going to be our condition to catch that top code there, okay? Right, that's checking single element intervals is how you're going to think about that, right? If the search interval has been narrowed down to a single element because before estimating the position, we handled a special case where there's only one possibility left, a nice little edge case in here, right? So that's what's happening here. If the single element matches the target, we return its index. Otherwise, we return -1 to say, hey, boss, ain't nothing here. There you go. So now the next and more difficult fun part here is calculating or estimating the position. So we're going to say let position equal low value plus math floor. And I'm going to explain this here in just a second, so maybe just kind of code it along and listen, and then we're going to sit back and try and digest what the heck is happening here. Because there's I have to read my notes on this because normally I can memorize these pretty well and go through after like an attempt or two on recording, but this one's going to require some effort here. Two sets of parentheses now. 2 times now, y'all. High minus low is this inner parentheses. We're going to divide that by our value at the high position subtracted by our value at the low position. So there is one of our 2 calculations. So this will be order of parentheses first. Take the high index, subtract the low index. Then we're going to take the high value, subtract the low value, and then divide those 2 values together, which should be this set of parentheses. Then we're going to take that and multiply it by our target subtracted by the array's low value, and that is our position estimation calculation, right? So it estimates the target position. We're going to use the distribution of the values in the current search interval, because remember we're going through iterations here, to estimate where the target might be. Again, this is how we're going to say, well, I know falafel starts with an H. Let's kind of just skip from the middle of the dictionary like the binary search would do and go to the F's and go from there. This is what this is simulating in that case, right? This is the whole probing positions on value distribution, not just the midpoint, and that's what this calculation does. So again, go into my notes because I had it more explicitly written here, because math is not, I'm pretty good at algebra and stuff like that. I always liked it in school. Again, I'm like 16 plus years outside of any kind of scholastic program, outside of this boot camp. I mean like traditional academia. And yeah, I took like some basic algebra and early calculus, but didn't really have to go beyond that for my major at the time. So I'm okay at it, but not great. So this is going to have to be a bit more note reading than normal. So I apologize if I'm kind of distracted, but I want to make sure y'all get this, and then I can teach y'all this a bit better from my notes. So here we go. Like I said, the target minus array low portion. This determines how far the target is from the lowest value of our current subarray. Because remember, we're honing in a range here. So we're going to see how far away the target is from our current low range, right? If the target is close to the low range value, this value will be small. If it's close to high, it's going to be large. So this is how we determine how close we are, right? Then the value high minus value low. This calculates the range of the values in the current region we are searching, our little subarray, we can think about it. It gives us the difference between the highest and the lowest values. Then this is kind of self-explanatory, high minus low. This calculates the size or the length of our region that we're calculating here, right? So once we've honed it in, we're like, okay, here's about the estimated region we're going to be honing in here. This calculates the length of that subarray. This determines how far away we were in the range or how big the range is, and this will calculate the range of the values in the given subarray. This determines the length of the given subarray, aka our estimated portion we're begin searching into. So we multiply our value density, this ratio first, because this division is going to be important. This division we're looking at is a ratio, right? A numerator and a denominator. The ratio computes how many indices correspond to each unit of value in the subarray. So think of it like value density. That's the big keyword I learned here. How many positions do we traverse in the array for a single unit change in the value? Remember, these are indices, how many we can traverse. This is the range of values, aka the ratio. How many indices can we move for a single unit change in value, right? Then we take that and multiply it by this value, which gets us the value density by the difference between the target and the low value, gives us a pretty good estimation of how many indices we need to move from the low index to get closer to our target, right? And then we add, this is the fun part here that took me forever to remember and understand, so I put big, bold notes, don't forget this idiot. We then add, I insult myself in my notes, what can I say? I like self-deprecating humor. We then add the offset from the low index to get our final estimated position of the target value. So I do have this explanation. If you want this, let me know. I can put it or pin it in the comments down below. Or if anyone has like a source that links a better mathematician explanation of this that can help, especially with visuals, please let me know in the discussion down below. I didn't find a good one that I liked, and I thought I could do better. And then my arrogance was your arrogance was my downfall. But yeah, basically, if you have to just memorize this for an interview, I know that sucks to say, but that is what it is, and I probably would have to as well, right? Anyway, that is what this position estimator can do. Let's go back to actually writing JavaScript code and trying to solve this, rather than trying to spend forever explaining the math behind this. This is going to be our best JavaScript estimation of, again, flipping towards the F's in the dictionary if we know we're looking for the word falafel. We're going to go ahead and just hone in our range to be much smaller than an arbitrary midpoint like we did inside of You guessed it, binary search. So we're going to say, hey, if the array at our calculated position is our target for this algorithm, then guess what? Not pause. Yeah, pause. Then we return the index, which is our position variable right here. Remember, it represents an index, right? So, hey, if we estimate and it happens, the estimate we did just happens to land on what we're looking for, hey, then we're good to go. Otherwise, we got to do some more calculating. We're going to say, if the array at our estimated position is less than our target, otherwise do something else. Okay, so here we go. If it is less than our target, that means we can move the low up. So we're going to say take the low and move it up to where the position is +1, because basically we're going to eliminate everything before that, right? Then otherwise, we're going to say high equals pause -1 to get our new end range, right? So that's how what we're gonna define as adjusting our search boundaries. So we're gonna say adjusting search boundaries. It's a very similar thing to what we did in the binary search algo that preceded this video, right? So if it's less than the target, we need to continue our search to the right since our estimate was too low. I think I might have said that incorrectly when I typed it. Typing and talking is hard, y'all. Doing this for a living has been very illuminating on what difficulties there actually are when coding and talking at the same time. Anyway, so again, this says, okay, we're less than our target, so we need to shift everything to the right because we're still behind what our target is. So then we can say, well, everything behind that's too low, so let's take our low boundary and bump it up to where our position was +1 and keep searching to the right and do the same algorithm here. Otherwise, the opposite is true. If it's greater than our target, that means we know that we can hone in the right-hand boundary of our search here by taking the current position, subtracting 1, and moving our high. I don't know why I keep typoing this. It's not written that way in my notes, but my brain wants to write low and high like that for some reason. I don't know why. And I like that because I'm not using TypeScript, it doesn't throw an error when I do that. Okay, so that right there is our conditioning, right? So basically, we can safely exclude from the positions to the end from our future searches. That's what that does. It moves in the right-hand boundary because we're like, hey, this is too far. This moves in the left-hand boundary or the low because it's, hey, it's too small. So let's go ahead and eliminate all of those right there. And that's what's going on. And that's basically what we got going on. And it'll keep on moving the boundaries until we either find our target or not find our target, or if everything gets out of here, then we have this final, hey, -1 because we couldn't find it. So let's see if I can get this working. And we're going to call Interpolation Search and pass in our input array right here and a target of 80. Let's see if this works. Hey, we got 7. Is that correct for 80? 0, 1, 2, 3, 4, 5, 6, 7. Let's go. That right there is our solution. This one's far more complex. I'm just going to put the recursive solution in the CodePen because I want y'all to focus and get comfortable with understanding this one rather than trying to mix it up with a recursive solution and get all complicated. I think binary search is a bit easier to understand, which is why I had no qualms putting it there. So once again, on our initialization, we have a low of 0 and a high of 9 since the array is 10 units long. That's what we're looking at right here, okay? So during the first iteration, after that initialized values, our first iteration, aka this while loop, says, okay, is this condition true? 0 is less than 9. Yeah, okay, cool, no problem. And the target lies between the array low and the array high. So the array low would be 10. The array high would be 100. Let me move this array, again, since we're talking about subsections and stuff. Let me move it into a comment up here. So here we go. Don't need this much room for the console log. Yeah, so, our array low is 10 on the initialized and first iteration. The array high is 100. Our target of 80 does fall in between that. So this is true. It's time to keep searching. That's our first iteration, right? So both are true. So we enter the loop. Inside of the loop, we check if low is equal to high. 0 is not equal to 9, so we skip this section entirely. Then we calculate the position, right? We plug the values into the formula. And believe it or not, on this example, this gets us 7. Thus, our position ends up being 7, right? So, can I demo... Oh, what did I just do? What am I done? Okay, let's try that again. Calculate and console log pause, please. Yeah, so this is a dumb example for my first one, because this is one iteration and it's done. But hey, look at that. It said, okay, let me take these current values. Remember, our high and low is high of 9, low of 0. Our array high is 100, our array low is 10. So we get 9 minus 0 is 9. This gets us 100 minus 10, which gets us 90. 9 over 90, I'm not going to do that, multiplied by target, which is 80, minus 10, which is our low, which is 70. So, 9 over 90, parentheses, times 80, right? And that math.floor, adding back our low index, which is still 0, gets us a calculated or estimated position in this distributed array example of 7. Then we're going to say, is the value at position 7, which is 80, equal to our target of 80? It is, and therefore none of this actually fires because there's no point in adjusting it because we found it on the first iteration. And there you go. That was easy enough. Let's go ahead and throw in low, high here and target into my console log so we can see this here, right? So yeah, there is our values here and our return value. Index of value, just like we did in the other one. That's right. There we go. So, yeah, I mean, it worked off of one iteration, and that's pretty awesome. It efficiently estimated the position and found it pretty quickly here. So this is a really short dictionary. Let's try and break it down for the second one here, and then we'll wrap it up for this video, folks. Same target of 80 to keep my life simple. The return value we're expecting is 17 if this worked. Let's go plug in this new value down yonder, format and save this document. Let's go 17, and I found it in 2 iterations. Dude, this thing's pretty baller, I gotta say. That's impressive. I can't find it in 2 iterations. So we're gonna paste this comment up here to remind us what our array input looks like. So here we go. Our initialized function has a low of 0 and an array length of 21 since the array is 22 units long, right? And then it checks the condition. Is low less than equal to 21? It sure is. Is our target of 80 greater than the lowest, which is 10? It sure is. Is it less than 100? It sure is. Therefore, it is all true when we run into our first iteration. Our low is 0, our high is 21, so we skip this conditional check right here, and we calculate our position. So that's what we're looking at right here, our calculation of position 16. We plug in the numbers, so we would get 0 plus math.floor of 21 minus 0, divide by 100 minus 10. Then we're going to multiply that by 80 minus 10. That gets us 21 over 90 times 70, and we floor that to get approximately 16, hence why we get pos 16. So then we say, finally, we get this time it doesn't find it right away. At position 16, is what? I believe it's 78 is our 16th position. I'm not counting that out. I'm just looking at my notes. That is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we got 78 on our first estimated position. That is not our target, which means we skip this check, and now we adjust. So we check the position, 78, against the target. 78 is less than 80. So instead of having a position low of 0, we take the position of 16 and add 1 to it. So it goes from, you guessed it, from 78, which is our position, 16, plus 1 to get 17, which is position 80. Which means it comes up here and checks it. Is our low position of 17 less than or equal to our high of 21? No, so it skips that. It recalculates the new position, which gets us a new position guess of 17, right? Based on the calculation of the new low of 17. This is what changed here. And then from there, it says if the array at position 17 is equal to our target, which is 80, which is true, therefore we get return our position of 17, right? So that's what happens on that second iteration. It does actually calculate this out to get 17, right? Because this check still passed. It was not the same positioning, so we calculate a new position and we plug in the numbers. It was 21 high minus the low of 17, our updated position. Make sure you recognize the low is 17 as well. Divided by our 100 minus 80 in our new range, times 80 minus 80, right? So we get if we multiply all that by 0 and we round 0 down, right? Then we would get exactly 17 because it's 17 plus 0. Because no matter what all this calculates to, it doesn't matter because this right here, the target of 80 and our current low value at 17 is 80 is 0, which means everything multiplied by 0 is 0. We simply add 17 back to our position. So 17 plus 0, hence why we get this console log here. And then right there, that condition ends up being true, and we got our example. So yeah, I'm going to close the terminal here so y'all can kind of stare at the code. Remember, it will be available in the CodePen as well, but this rounds it out for this video, and I'll have the recursive solution in there because I think 30 minutes on this alone is enough without melting our brains. So a fair bit more complex than binary search, even though it seems like it'd be easier going, oh, just estimate and move on from there. If you just have to memorize that little thing right there, then so be it. But, you know, things like phone directories, music libraries, digital publishing with tons of e-readers with large books or collections, data analytics, GIS, any kind of geographical information systems and applications where you have like latitude and longitude, those values tend to be sorted and you want to quickly find all the points of interest around a given coordinate. Interpolation can help narrow down the search region much faster because you have a good estimated guess and the values to find around that. Some databases distribute data across nodes based on the value of the data, aka using consistent hashing. So when you're querying for a specific piece of data, Interpolation Search is great for distributed databases. Financial markets and gaming, especially in games with large open worlds, you have certain objects or characters might be sorted in a similar manner based on their position in the world, aka probably an uniformly distributed data set. In Interpolation, searching can quickly fetch all the objects near a specific location because you can hone it down in that dictionary of the open world, for example. So yeah, thanks for tuning in. I hope this exploration into the world of Interpolation Search was fun. I had a lot of fun making this video and researching it. I learned quite a bit on the way myself. It's not like I just magically knew this. I knew of it, and then I tried to code it myself, which is what y'all should be doing, and then I researched how to not only solve it, understand it, and be able to understand it well enough to hopefully explain to y'all in this video. So hopefully you appreciate it. Remember, constructive and positive comments are well appreciated here and welcomed here for all of us to be growing together on this journey as developers. Remember, they're building blocks for coding in the real world, and mastering them is part of acing those coding interviews. So see y'all in the next video.